Welcome everyone. Myself Riya from Sri Venkateswara College of Engineering from CSE Data Science Department. Today I'll be giving a presentation on the topic of pumping lemma from the subject. Welcome everyone. Myself Riya from Sri Venkateswara College of Engineering from CSE Data Science Department. Today I will be giving a presentation on the topic of pumping lemma from the subject Theory of Computation, also known as TOC. So first, let's understand what is the meaning of pumping lemma. Pumping lemma, it gives a method for pumping or generating many substrings from a given string. In other words, we can say that it provides a mean to break a given long input string into several substrings. It gives necessary conditions to prove a set of string is not regular. So regular means it is a type of language that can be recognized by a finite automation and is defined by a regular expression. Let's understand the theorem. For any regular language L, there exists an integer p such that for all w in L, where mod of w is greater than p, we can break w into three substrings. As we know, the main agenda of pumping lemma is to break a given long input string into several substrings. W is equal to x, y, z such that the mod of xy is less than p, the mod of y is greater than 1, and for all k which is greater than 0, the string x, y and y to the power of k, z is also in L. So let's understand what are the applications of pumping lemma. Pumping lemma is to be applied to show that the certain languages are not regular. It should never be used to show a language is regular. If L is regular, it satisfies the pumping lemma. If it does not satisfy the pumping lemma, it is not regular. Let's look into the steps to prove that the language is not regular. So the step 1 is that we have to assume that L is regular. Step 2, the pumping lemma should hold a value for L. Step 3, it has to have a pumping length, let's say P. Step 4, all the strings longer that P can be pumped where W is greater than or equal to P. Step 5, now find a string W in L such that the W which is in mod is greater than or equal to P. Step 6, divide the W into X, Y, Z, that is a string into substring. Step 7, show that X, Y or to the power of K, Z should not be equal to L for some value of I. Step 8, then consider all the ways that W can be divided into X, Y and Z. Show that none of these can satisfy all the three pumping conditions at the same time. These are the conditions that needs to be satisfied. Step 10, W cannot be pumped, so that is equal to the contradiction. It shows that the language is not regular. Let's look into the disadvantages of this pumping lemma. First is it cannot prove regularity. The pumping lemma can also be used to prove that the language is not regular. Even if a language satisfies the pumping lemma, it does not guarantee that the language is regular. It is not a bidirectional tool. It means that it satisfies the pumping lemma is a necessary condition for a regularity, but not a sufficient condition. Some non-regular languages might accidentally satisfy the pumping lemma in a specific case. The third disadvantage is dependent on a string decomposition. The proof relies on splitting a string into x, y, zx, y, and z parts. In some cases, determining a valid split for x, y, x, z, y, and z can be a tricky or ambiguous. The fourth disadvantage is ineffectiveness for some non-regular language. The pumping lemma is not the only tool to prove non-regularity. Some non-regular languages can be easily proven non-regular using this lemma alone. Other methods like Myfil-Nerodom theorem are required. The fifth disadvantage is limited applicability. It is specific to regular languages. For other classes of languages, for example, context-free languages, different tools like pumping lemma for context-free language are required. The sixth disadvantage is counterexamples can be difficult to construct. Finding an appropriate string SS and showing a contradiction can sometimes be a non-intuitive or require creative thinking, especially for complex languages. Let's look into an example to understand pumping lemma better. Here we need to prove that L is equal to a to the power of I or b, and b to the power of I, where I is greater than 0 is not regular. So the solution, at first we assume that L is regular and n is the number of states. Let W be equal to a to the power of n and b to the power of n. As you know, the first condition, the mod of n should be greater than the combinations of this. That is n plus n, that is 2n should be greater than n. By pumping lemma, let us divide the value of W to x, y, and z, where the mod of xy should be greater than n. Let x be equal to AP, y is equal to AQ, and z equal to AR and BN, where the summation of P plus Q plus R will be equal to N, where P is not equal to 0, Q is not equal to 0, and R is not equal to 0. Thus, it implies that Y is also not equal to 0. Let the value of K be 2, then x to the power of x, y to the power of 2, z will be equal to a to the power of P, a to the power of 2Q, a to the power of R, and b to the power of n, where we are basically uh, implementing or substituting these values. Number of AS is equal to P plus 2Q plus R, which can be further calculated to or formulated to n plus q. Hence, the value will be finally equal to a to the power of n plus q, b to the power of n, since q is not equal to 0, and it is here the value is not in the form of an and bn. Thus, we can conclude that x, y to the power of 2z is not L, hence L is not regular. That's all with my presentation. Do like, share, and subscribe.